This video we'll be dealing with black body radiation. What does it mean? Well, first things first, what is a black body? Now, as you know that you are able to observe few things when a light falls on them and then is reflected back to your eyes. So this is a simple way of observing things. That's how nature works. Now, supposedly, this object is supposedly green in color. Now, what it does is that of all the rays that fall on it, the rays obviously that fall on it are white light comprising of all the constituent colors, and out of that, with this surface, what it does is it reflects the green wavelength to your eyes, and as a result of that you are able to know that this is a green surface, or the color of the surface is green. Now consider the case where the object that you're observing, what it does is it just takes in all the light that is falling on it, and it doesn't reflect any particular wavelength. So although it reflects, but the reflection is not in the visible range, not in visible range, or you can say that it has it has given out no particular wavelength that you can observe, and that is why it is completely black. That is a black body. And the general black body that we will be discussing today, that is simply a kind of body which can take in all the wavelengths that are incident on it without giving it back, and as a result of that, because it is not giving out any radiations, it is not reflecting uh, at that instant of time, it is not reflecting immediately, so that body is now a black body. There are many theories about the construction of a black body. Well, you have no such perfectly black surfaces, though you can theoretically construct one. What you may do is that you can consider a cavity, a shell with a cavity, and you can just cause a light to be incident into that cavity, and it goes through it strikes a spike, so as to say over here the spike is so adjusted, or so well maintained at that point, that it goes through multiple amount of reflections in within that object or within that body, and it just doesn't return the light back to you, and as a result of that, with these multiple reflections going within the body, you are unable to get back a signal, the signal that you expect to get back from that cavity. So there is no escaping of that light at as quick as at that instant that you may consider. So as a result of that, this is a theoretical or hypothetical black body. Now, what in case we have the black bodies, so what we can expect? Well, we can expect that there will be radiations which will be incident on it, and it will be absorbing all sorts of radiations from all possible directions, and as a result of that, it will increase its energy, because the radiations, they are electromagnetic radiations, they carry certain amount of energy, and with absorption of energy it will raise its energy, internal energy, As a result of that, what happens is that it raises its temperature as well. But the surrounding that encompasses the black body, the surrounding must be having a certain temperature, and the black body is restricted to some extent. It cannot go on absorbing all the energy that is incident on it for every for the eternal time. uh, it can absorb the energies up to a certain limit till it achieves thermal equilibrium. Thermal equilibrium means that it is now at same energy level or same temperature with respect to the surrounding surrounding atmosphere, that is with respect to its immediate surrounding. And because why is that so? Well, because that it is according to it is in accordance with the second law of thermodynamics. Because if it goes on absorbing those energies, and the surrounding temperature goes down, the temperature in the surrounding goes down while its temperature over here it goes on increasing, well, that violates the second law of thermodynamics, and as a result of that it cannot do that. It cannot violate a law for sure, and that is why its temperature increases, or it goes on absorbing radiations up to a certain limit, that is up till it achieves the thermal equilibrium. Now, because it has achieved thermal equilibrium, now that it has gained a certain amount of heat with all the radiations absorbed, now it can give out radiations. Well, because it has absorbed all the radiations, it is capable of giving out all the possible radiations, which means all the possible wavelengths. Now, as you know, the radiations that were incident on it were electromagnetic waves, so it will be giving out a whole range of electromagnetic waves, and which is essentially the work of any object that absorbs the light, that is, or absorbs the radiations that are incident on them. They give away those radiations. Even we as human beings, even every object that we see in day-to-day life, they, when the energy is incident on them, they absorb it and they tend to emit it as well. There are certain wavelengths associated with everything, but however, this is not the same case as reflection. This is the case of absorbing the lights and absorbing the radiations and emitting them. The reflection is from the surface, but the absorption of the energy is obviously from within, and you give away the excited molecules of any object. They absorb these energies, they get further excited, and then they give away those in the form of electromagnetic radiations. Now, the emissive power of a given body can be uh, expressed. This is the emissive power of a given body, and this is within a wavelength, or this is at a given wavelength lambda. Emissive power at a given wavelength lambda. And this emissive power is nothing but the energy. Obviously power is energy radiated per unit time, and this is the energy that is radiated per unit time per unit area. So this is the energy that is radiated per unit time per unit area within a given range of the wavelength. And if we are to obtain the total emissive power of any given body, total emissive power, then that will be denoted as simply E is equal to the emissive power at a given wavelength over a whole range of wavelength, where the integration is over the entire range of wavelengths available. Now this obviously is in watt which is energy per unit time per unit area, means watt per meter squared. The different surfaces will obviously have different emissive powers. For a given surface, the emissive power changes with respect to temperature. Then we have the absorptive power. Now the absorptive power is simply we can take it as the ratio of the energy that is absorbed by the surface. Obviously all the radiations that are incident, they fall on the surface and then they are just absorbed completely into that body. So energy absorbed by the surface per energy incident on it. So this is more or less the absorptive power, and in case of black body, as you know, the absorptive power is going to be 1, because the black body has the tendency of taking in all the radiations that are incident on it, that is all the energy that is incident on it, and it absorbs all of them completely. So that in case of a black body is 1, and for rest of the bodies, the general bodies that we find in our day-to-day lives, they are obviously less than 1. Now another thing that we can relate is that the absorptive power, now the emissive power, first of all, that we have discussed earlier, that the amount of energy that is radiated, obviously it is emitting the energy, so the amount of energy that is radiated per unit time over a range from lambda to lambda plus d lambda can be given by this. Now if we have supposedly a surface which is in the form of an enclosure, and it is maintained at a constant temperature T, and it has supposedly an emissive power for this surface is E lambda over the given range lambda plus d lambda. So it is emitting E lambda times of d lambda, that is the amount of energy that is being radiated per unit time per unit area from the surface. And now it has a body inside it, and this body supposedly has an absorptive power of A lambda. A lambda is the absorptive power of this body which is placed inside it, and E lambda is the emissive power of the enclosure. Now obviously this enclosure will be giving away the radiations or the energy to that body, which in turn will be absorbing them. Now if dq is the radiant energy that is incident per unit time per unit area, then the energy absorbed per unit time per unit area will be obviously equal to A lambda times of dq. This will A lambda times of dq will be the energy that will be absorbed. And with that amount of energy absorbed, obviously it will be absorbing that amount of energy that was given to it, and the energy that was given is obviously this one, that is E lambda times of d lambda is equal to A lambda times of dq. So what we have over here is a ratio of E lambda over A lambda, that is the emissive power to the absorptive power, and that is equal to dq divided by d lambda. Now consider the case of a perfect black body. Now the perfect black body, for the black body, let the emissive power that it has is denoted as capital E lambda, and we know that the absorptive power is equal to 1. Now if we use this particular equation for the black body, then what do we have? If the black body was placed inside that object, then the inside another black body, then we would have had E lambda d lambda is equal to 1 times of dq, 1 being the absorptive power over here. So dq divided by d lambda will be equal to simply E lambda, that is the emissive power of the black body. So with these two being the same, we can relate the other two terms that I have just encircled, that is E lambda, that is the emissive power of any given body, to the absorptive power is equal to the emissive power of the black body. Well, we would have had the absorptive power for sure at the denominator, but in case of black body that is equal to 1, so we just have to be contented with that E lambda that is over there. And this is the Kirchhoff's law of radiation. So the Kirchhoff's law of radiation states that the ratio of the emissive power to the absorptive power for a given wavelength is the same for all bodies, and it is also equal to the emissive power of the black body. Well, it is equal to actually the emissive power of the black body to the absorptive power, but as you know that is 1, so this will be simply equal to the emissive power of the black body. And this also goes to tell us that as it is the same, it is constant for all the bodies that are involved, then it also tells us that the good uh, conductors or good absorbers are also good emitters, and vice versa, where good emitters are good absorbers of energy. Moving ahead, if we consider a black body radiation in a cavity of volume V, and it is maintained at an absolute temperature T, then the behavior of the black body is taken similar to that of an ideal gas, and the laws of thermodynamics are applied over here. Now, if U is the energy density of radiation in cavity, then because the black body radiation is diffused radiation, it is a diffusion form that is taking place, diffusion of the radiation, then we have the pressure on the enclosure to be given as the energy density of radiation divided by 3, as per the laws of thermodynamics, as I said. Now, the total internal energy U will simply be equal to the energy density, that is per unit volume, that is the energy per unit volume, multiplied with the total volume, that is V. Now, if dQ is the amount of heat that the system absorbs, then the internal energy and the volume change by, so dQ is the amount of heat that is being acquired, so the internal energy changes by du, while the volume by dV. And from the first law of thermodynamics, what we have is dQ is equal to du plus P dV. And also from the second law, we have dQ to be equal to T times of ds. ds is the increase or the change in entropy of the system. So we just substitute this value up there, and what we get over here is that Tds is equal to du plus P dV. Now, this can be written in the form of partial derivative, where we have T del S by del V equals to del U by del V, and obviously dV dV, that goes to 1, so we are left with P, and all of that at a constant temperature T, which was maintained over here. And we can use the Maxwell's thermodynamical relation over here, where del S by del V goes to del P divided by del T at constant volume. This is from Maxwell's thermodynamical relation, and the T stays as it is. So this is equal to del U by del V at constant temperature plus pressure. And with all of that available, we can just put the values that we had obtained here. Remember, P is equal to U by 3, so this is simply U divided by 3 del by del T of U by 3 at constant temperature, sorry, at constant volume. And then we have for U we can use this value, that is, this is the total internal energy, of course, and we are going to use del by del V of U times of V, V being the total volume as I mentioned, and that plus U by 3. So what this gives us is, this is the 3 can be taken out and it's a constant value, and so we have du by dt, and then we have over here del V cancels out to 1, not actually cancels out, it operates on V, and so we have just U left over here and the U by 3 that was there. So this equates to 4U divided by 3. So then we have dt over T can be kept on one side and the 4 can come up over here. So 4 dt by T is equal to du divided by U. And so what we can have is simply, we can integrate these terms. What we have is U, this is ln of U, and that will be equal to ln of T, 4 times of ln of T, plus some constant which can be taken in logarithmic form as well. So ln, let it be alpha. So this will be equal to ln T raised to the power 4, as is the case with logarithms, and the alpha can get multiplied with this, the constant value, and ln U is on the left hand side. So what we get is the energy, that the energy density that we had mentioned, and that is equal to some constant times of the absolute temperature raised to the power 4. This is known as, well, that constant that we have, it will have some value. The energy density is directly proportional to the total energy that is radiated per unit time. So if I say that this is R, that is the total energy radiated, or the power radiated, energy radiated per unit time is power radiated, radiant energy, or radiance as we call it. So from the unit surface of area of the cavity, this will be proportional to the fourth power of the temperature as well. And now this radiated energy is equal to some constant times, which is sigma of T raised to the power 4, and this sigma is what we call as a Stephen's constant, and this is the Stephen's law. And Stephen's constant, I like that number because it's very easy to remember, because the number has 5, 6, 7 and then 8. How is it written? 5.67 times of 10 raised to the power 8. Well, it's actually a minus 8. And because this is the power and this is the temperature, and so this is the power radiated per unit area, so watt per meter squared per Kelvin to the power minus Kelvin to the power minus 4. So this is the unit of Stephen's constant, which has the value 5.67 times of 10 to the power minus 8. Stephen's law of radiation. If the external the external surrounding, that is in this case supposedly if it has a temperature of, this has a temperature T, the exterior points or exterior region has a temperature T0, not to the power 0 but T subscripted with 0. So then the it'll have a radiance of r0. Now the amount of heat that is to be radiated to the surrounding by the black body per unit time can be given as this equation, that is r minus r0 is equal to sigma, which is a constant of course, times of t raised to the power 4 minus t0 raised to the power 4. And this is in accordance with the Stephen's law of radiation. Now, as mentioned earlier, if the black body is absorbing all sorts of radiations that are incident on it, it must be capable of radiating frequencies or wavelengths over the whole range. And so we can have an energy distribution. We can plot an energy distribution curve for the black body radiation, and it will be pretty straightforward, is what we expect it to be. But let's see if it's like that or not. So this is the energy that is being radiated at supposedly at different wavelengths, and the wavelength axis lies in this direction over here. Now, as we consider the radiation, what would have happened is that the wavelength, the radiation would have continued in this form. Now, this is quite expected because we are expecting this, because we'll be getting all sorts of wavelengths and with equal intensity or equal power. The emission will be for all the wavelengths equally, because it is equally absorbing them. But that is not the case. What we observe is something different. The observation is in this form. Where the energy is increasing up to a certain wavelength, and then it decreases. And this denotes the maximum wavelength, and this is at a given temperature. Let us suppose this is T1. Now, this is quite different from what we have expected. Furthermore, if we continue with the experiment at different temperatures, what we find is this is supposedly lambda m1, which is the maximum wavelength corresponding to the given distribution, or the wavelength corresponding to the maximum point of the distribution. And then if we are considering a lower temperature, then we'll be getting something like this, where T2 is the temperature still lower than T1, and the peak value obviously has reduced a bit. And then further, if we go down with the temperature, we again get a shift at the peak point, as well as the case where the peak value is pretty less. Here we have T1 to be greater than T2 to be greater than T3. So what we find is that the maximum, or the wavelength corresponding to the maximum, that shifts with the shift or the change in temperature. As the temperature increases, the maximum wavelength decreases, is what we find, because this is lambda m1, as you know, has a value which is less to lambda m2, and it is still further less than lambda m3. So the wavelength corresponding to the maximum value, that goes on decreasing with the increase in temperature. This was given by this relation. If you multiply that corresponding wavelength to the temperature, then we get that as a constant, and that constant is known as or is of the value 2.898 times of 10 to the power minus 3 lambda meter and temperature Kelvin. So this is a meter Kelvin, not to be read as milli Kelvin. This is meter Kelvin, and this is the popular Wien's displacement or Wien's displacement law. Now, as you can see, the displacement term suggests that the wavelength corresponding to the maximum value in that distribution is displacing or shifting across the plot. Then we have the Wien's radiation formula, where it was given in 1896, where it is corresponding to a certain frequency we can give as an empirical formula which was given by Wien, and it was let me spell that correctly. This is Wien. So Wien's radiation formula, and u nu d nu, which is the frequency range d nu, the energy that is emitted, or the energy that is energy density we have in that frequency range, to be given by A, which is some constant, times of nu cube e to the power minus b, which is again a constant, times of the frequency nu divided by kt multiplied with d nu. So this is the empirical relation given by Wien radiation formula. So u nu here is obviously the radiation or radiant energy, which is per unit volume per unit frequency, taken from the range nu to nu plus d nu. And k here is the Boltzmann constant, (1.38 times of 10 to the power minus 23). This is what is the value of the constant, Kelvin inverse. And if we are to take this in case of the wavelength, as you know, wavelength is related to the frequency as nu is equal to the frequency that is equal to the speed of the electromagnetic wave, which is equal to c divided by lambda. So if we are to take d nu, we'll have to take it as minus c by lambda squared d lambda. So we just substitute that value over here. So instead of lambda we have, instead of nu we have c cubed divided by lambda cubed, and this is e to the power minus b. This is c, that is the speed of light, divided by lambda kt, and this is c by lambda squared. The negative term over here, well, that negative term can be taken outside, so this can be taken over here, and this suggests that the frequency, as the frequency increases, obviously the wavelength decreases. So we can neglect that term, that negative sign from this part, and we are just left with a c raised to the power 4 lambda 5 e to the power minus bc divided by lambda kt d lambda. So this is giving us some constant value, let us say that is a, lambda raised to the power 5 e to the power minus some constant b divided by lambda kt d lambda, because b times of c is again a constant, because c is the speed of light or speed of an electromagnetic wave, which is always a constant, 3 times of 10 to the power 8 meters per second. Now this formula that he gave, well, although it was very well accepted for the high frequency terms, but was in violent disagreement for the low frequency terms. As you can see, low frequencies means higher wavelength. Well, you may say that the higher wavelength over here, as the wavelength goes on, the value is decreasing, and here we have lambda divided by lambda to the power 5 in the denominator. So what's wrong with that? With the wavelength increasing, the value is decreasing, but that's the we haven't really integrated that with the integration term coming up, that lambda that is there in the power of E over here, this one, well, that will be multiplied because it is in the reciprocal of that power term, and as that goes or gets multiplied, the value goes to infinity as well. So one would expect that the value goes on increasing with the higher wavelengths, but that is not the case. So this is in complete disagreement with the low frequency or high wavelength range. Then comes the another empirical relation which was given by Lord Rayleigh and James Jean, which is the Rayleigh-Jeans formula. And according to that formula, what we have is that this, with respect to the frequency range, this radiant emission is equal to 8 pi nu squared divided by c cube kt d nu. This again, well, this term failed to explain if this failed in a low frequency region, this was able to explain the low frequency but failed in the higher frequencies. What exactly happens over here is that for the higher frequencies, when you have the wavelengths to be very less, this will go to infinity, of course, because the value goes back like this. Let me give you an idea of what exactly. Thank God it doesn't go that way. Why? Because, well, if you see that if they are going backwards like that, that means the energy is increasing. And energy is increasing for lower wavelengths. Now, what are the lower wavelengths? The lower wavelengths are the ones that you get with the higher frequencies, that is for the ultraviolet, the X-ray, the gamma rays, right? And in those cases, it's by nature it's defined like this, that it will go down the curve. The nature of the curve is going down. We are just explaining that. But what if it had not gone down? Things would have been really terrible for us, because consider the case of a room heater. The electric heater that is present in your room, what happens is that if you observe it, then for the higher wavelength regions, it starts off over here. The higher wavelength region, that is the infrared region, right? In that infrared region, you start, when you switch it on, you start to feel the heat even if you don't see it, because it's not in the visible range, it's in the infrared range. You will have to wear special lenses for that, the infrared goggles, that is. Then it comes down to the visible range, suppose, and in the visible range you are able to view that when you observe it to be in crimson red, and then finally a reddened form. And then again, what happens is that as it goes towards that ultraviolet region, it drops down like this. So it starts off like this, it goes on increasing, and then with this formula it would have continued in this fashion, but as it approaches that ultraviolet region, it drops down, and that is what is termed as the ultraviolet catastrophe. Now, although it's a catastrophe, but it's a good one, because had that energy went on to increase in that fashion, in the backward direction, as indicated by those dashed lines that I'm drawing over there, then the energy would have been really high, out of proportion, and you might have just burnt yourself. So it's good that it does not happen, but still we haven't got a good explanation for all that is happening with the black body radiations. We'll be providing a answer to that, which has been already provided by Max Planck in the year 1900 with his famous Planck hypothesis, which was then proved by Sri S.N. Bose, the famous Indian physicist, our very own S.N. Bose, and using statistical mechanics, of course. And then we can obtain a relation, certain relation, which is going to help us understand this black body radiation, the formulation of the black body radiation, and a very special one because it also gave birth to the concept of quantum mechanics. The very seeds of quantum mechanics were sown by this kind of an approach taken by Max Planck. So that is for the next video. Till then, thank you for watching.